So, today we will have a look into how after the data is made ready by carrying out gravity data reduction, the data is now ready for interpretation. So, today we will have a look into how the data can be interpreted. So, gravity data interpretation can be done initially by preparing what is known as gravity anomaly maps. So, what is a gravity anomaly map? The data which we have obtained from the field after, of course, after gravity data reduction, the data can be directly plotted in the form of a figure as you see here. Right? What does that figure give? This figure gives the relative gravity measurements. So, here the survey, as we have seen previously, most of the gravity survey is done in relative mode. That means we keep one station as a reference station. With reference to that, we try to understand whether the gravity of an unknown station is more or less, how much, with reference to the reference station. I had also told you already, it is something like for a civil engineer, we do a survey, we do surveying. How do we do surveying? To understand the elevation difference, we keep one location as a benchmark. With reference to that benchmark, the relative level of a unknown location is plus 0.5 meter or minus 0.25 meters. So, this is how we write. Right. In the same manner here, the relative gravity measurements were made at this site, and here is the plot of how the gravity varied over this area, right. So, here all this green is like a base station, right. All the colors, especially blue colors, cool colors, negative, and all the dark colors, especially dark red and violet, they are positive anomaly. So, from the picture itself, we can understand the region which is having dense material, right. Here you can see you are in this. So, compared to the overall region, this region has got more denser material. Similarly, this particular region also has got denser formation, whereas the green region is more or less 0 or less. Similarly, if you look at the blue zone has got very low gravity value. So, this is how we carry on with the interpretation. This kind of interpretation is known as qualitative interpretation. That means, by looking into the gravity anomaly map, we try to decipher regions that are having dense rocks or regions that are having less dense rocks, right. Here these authors, right, have made use of gravity anomaly map and how the gravity anomaly responds to a major anticlinal structure, right. There is a anticlinal structure is like beneath the surface of the earth. I am drawing a cross section. This is the surface of the earth. Beneath the surface of the earth, the formations are folded like this. So, this is called as an anticline. The axis of this is something like this, right. When I draw a fold three-dimensionally, right, this is how it is. So, this is known as fold axis. So, this all these colors indicate the fold axis. They have demarcated the anticlines as well as synclines. Synclines are just reverse of this, where the formations are folded this way. This is known as a syncline, this is known as a anticline. So, this is how the interpretation can be made by looking at the gravity anomaly map to decipher locations having high denser rocks or lighter rocks. And here the denser rocks are more or less aligned along the anticline. Probably the topmost rock here is much denser, more density, right, or density is high, density compared to the formation just below it, right. So, this is how we try to decipher the formations as well as major structures by looking at the gravity anomaly maps. Boger anomaly maps are usually prepared, right, what we had seen on the previous page. This anomaly map actually include both regional as well as local anomalies, right. That means, what do we mean by regional? Regional anomalies have long wavelength and they are usually due to deep crustal features, right. Even features beyond 25-35 kilometers, right. They also induce some anomaly. We make the measurement at the surface of the earth with the aim to decipher some local phenomena, but this is getting masked by regional anomalies, right. So, regional anomaly is resulting due to even the variations in the Earth's crust. What is Earth's crust? This is the surface of the Earth. The Earth's crust is the topmost part of the Earth, which is about 35 kilometers in thickness. At some places it is 35 kilometers, at some places it may be only 25 kilometers, right. Beneath the oceans, obviously the thickness of the crust will be little less, and the composition of the crust and its thickness also affect the gravity measurements which we make at the surface. This effect is known as regional effect. These are the known as regional anomalies. Whereas local anomaly, or which is also called as residual anomaly, will have usually shorter wavelength because of shallow structures. That means very close to the surface of the earth, we may have something like we had seen on the previous page, a small anticline or syncline, or the density of the formations may vary closer to the surface of the earth. This also affects the gravity reading which we take at the surface of the earth. This anomaly is known as residual anomaly. Actually, in gravity exploration, our aim is to, most of the time, our aim is to understand the local anomaly. Not really. Sometimes scientists try to understand how the thickness of the crust varies with respect to time. So, pure geophysicists, their aim is to understand how the thickness of the crust varies, how the plates are responding. That means the plate continental drift theory, how the plates on the surface of the earth, that means the surface of the earth has got different plates. These plates also move over one another, right. For example, if you take India, it is known as Indian plate is colliding with Eurasian plate, which is in the north, just north of Himalayas. These two plates are actually colliding with each other, leading to growth of Himalayas, right. So, if you want to understand all these mechanisms, we are actually looking for regional anomalies. But in exploration, our aim is to understand, decipher different rock formations in a smaller region. So, over there, our interest is on residual anomalies. But when you make measurements, you have the combined effect of both regional as well as residual anomalies. So, that is what we see here, right. On the picture above, we have measured, right. This is the surface of the earth. On the surface of the earth, along a particular profile, we have made the measurement of gravity values. The gravity values actually varied something like this, right. So, the measured value which we have obtained is a combination of both regional plus local anomaly, right. That is what we are measuring during the field work. There are different techniques available which is beyond the scope of this subject, right. There are several filtering techniques that are available that help us to separate the regional from the local anomalies, right. So, such a technique has been employed here. Now, what we have done in this picture is, we have removed the effect of regional We have removed the effect of regional anomaly. We have removed the effect of regional anomaly in this, right. So, after removing the regional anomaly, whatever is the impact due to the local or residual anomaly alone is plotted in this diagram. So, this is what we are looking for, right, because what we can understand from here, at this location the density of the formations below the surface of the earth is high density rocks. Beneath this location, low density. Here too, high density. Why? Because the anomaly is on the positive side, right. Relative gravity measurements we have made is on the positive side, here on the negative side compared to the base station. So, comparatively low denser formation. So, this is how we prepare even the maps which we have seen on the previous page, right, is after filtering the effect of the regional anomaly. Only then this map help us to decipher major structures very close to the surface of the earth, right. So, how we have done that? We have done using some filtering techniques that help us to segregate between the regional as well as local. So, here in the top picture we see the combined effect of regional plus local. Here we have removed the regional anomaly. So, what we have only is the local or residual anomaly. That is what we make use in exploration, right, especially to understand about the shallow subsurface. Right. So, here the observed gravity value contains, right, all the major structures. So, here is an interesting example, right. There are techniques available to segregate the effect of each and every structure, right. In this study, these scientists have carried out a study and plotted the total observed gravity value, right. So, this contains information about all the aspects of the subsurface. So, this is the typical cross section, right, a hypothetical cross section. So, this cross section has got several sedimentary layers as you see here, right. And then at the center we have a major rock which is granites, which is a major igneous rock type. This rock has also subsequently has been intruded by a secondary intrusion which is known as dike, right. So, there is a massive granite rocks. Granite rocks are subsequently intruded by a dike rock, right, which is popularly known as dike, usually maybe of dolerite in rock type, and this is surrounded by sedimentary formations on either side. These sedimentary formations are also inclined, they are not exactly horizontal, they are inclined by an angle, right. There is an angle of inclination, right, maybe about 20 degrees. Over there we are carrying out gravity survey, we have made gravity measurements at the surface, right. How we have made relative gravity survey. What is relative gravity survey? I told you about the height of all of us, right. In relative gravity survey, we fix up one station as a base station. With reference to that, gravity value here is plus 5 milligauss, here it is minus 5 milligauss, here it is plus 10 milligauss. This is how we make the gravity measurements. The measured value are plotted here, the topmost diagram. So, base station is, let us say at the base station gravity value is 0 compared to the base station. Now, we have plotted the values of gravity. Everywhere the gravity values were slightly higher than the base station. So, it varied something like this, as you see in the dark black line. So, this is the total observed gravity signal. Of course, after gravity reduction, please keep it in mind, obviously we need to carry out gravity data reduction, only then the data is ready for interpretation. Now, there are techniques, as I had told you, available, right? Some processing need to be done to get the actual effect of individual formation. First, let us have a look into this profile where the effect of the dike alone. What is the dike? That is this black line which I am converting into red now, right? This is a dike rock. Usually dikes are more massive. The common dike rock is the black granites, which most of us would have seen in countertops or in tabletops or in kitchen counters. We see a shiny black granite. They are usually of dolerite type. They are normally found as dikes. These rocks are comparatively more denser than the granites, due to which when you take gravity profile over this terrain, imagine nothing else is present everywhere. Imagine everywhere we have granites everywhere, but only if we have one dike at the center. If you make gravity measurement at the surface, gravity value will be much higher above the dike and it will reduce, right. So, that is what has been picked up here, right. That means we have come out with what will be the gravity anomaly only due to the presence of dike, right. Then what will be the effect of granites? What will be the effect of granites is indicated here. What will be the effect due to dipping strata, right. So, here that is only because of the sedimentary formation. So, here what was the assumption we have made? The subsurface is something like this, right. This is the subsurface, the same box which we see here. I am drawing here, but I am removing all the other formations. What I am drawing is only the sedimentary formation, such as sandstone and all sedimentary formation. Of course, at the bottom we have some massive rocks. If you have something like this, the gravity profile which we will get is something like this. That is what is the gravity profile due to dipping strata, right. So, this is how we can segregate the effect of different formations as well as structures on the gravity value which we measure at the surface of the earth, right. So, there are tools available to segregate the effects of dike, granite formation and the dipping formation on the acceleration due to gravity, which we will measure at the surface of the earth, right. And here, as I was telling you at the beginning, first we have a look at the Boger gravity map. What does it refer to? We had seen this already. In Boger gravity map takes into account of regional plus local, right. So, what is the regional anomaly? Regional anomaly is due to deeper structures, especially what is the composition of the Earth's crust, whether the Earth's crust is thick or thin, that will also have its impact on the gravity which we measure at the surface of the earth. That is regional. Then within the shallow depth, maybe up to 1 or 2 kilometers or within 10 meters, 20 meters, the density of formations may vary, or there can be some shallow geological structures such as faults or major faults, they are going to exert some influence on the measured gravity, that is local. So, here we have both Boger gravity anomaly map, which includes regional as well as local, something like what we had seen here, right. So, here the profile we see in this profile, both the effect of regional as well as local or also known as residual anomalies are measured. Then using some technique, we have removed the regional effect and we have plotted just the residual anomaly, right. Similarly, here too, initially we had a map showing as the Boger gravity anomaly. Now, using some techniques, we have segregated regional as well as local. Here is a separate plot of only the regional anomaly. Here we look into the residual anomaly. So, in regional anomaly, we see the impact on the gravity measurement due to very large structures and also deep structures, maybe even the effect of the crust, right. Whether the crust is thicker, thinner will also has its impact on the gravity which we measure at the surface. When you remove the regional from Boger gravity, right, Boger gravity anomaly minus regional gives you the residual gravity. So, in residual gravity anomaly map, what we get is, right, what is the impact of the formation that are very close to the surface of the earth, right. So, this is how we carry forward with regard to the interpretation of gravity data by qualitatively looking at the Boger gravity map or residual gravity map, as you see in this slide, right. Now, we had a look into qualitative methods of interpretation of gravity data. Then the next is quantitative methods of interpretation. In quantitative methods, we try to estimate the approximate shape of the body which we are searching, right. Shape of the body which is buried below the surface of the earth. We are going to deduct that by making measurement at the surface of the earth, right. So, this can be done, right. We can try to understand what is the shape, what is its approximate size, at what depth it is located from the surface of the earth. So, if we are going to do something like that, then the interpretation is known as direct interpretation, right. Then the second method of interpretation is known as indirect interpretation, right. First, let us have a look into direct interpretation. So, what we have done is the anomaly in the gravity which we measure over differently shaped bodies has been established very well by different researchers, right. Imagine this is the surface of the earth. Beneath the surface of the earth, suppose if you have a sphere, right, whose density is high compared to the surroundings, right. This is the ground surface. You have a spherical ore body or a spherical body which is having high density compared to formations which are having lower density around that. Over there, if you carry out gravity survey, right, imagine we are doing profiling from here to here, and here is the plot of the variation in the gravity value. Obviously, gravity value will be high just above the spherical ore body because it is having higher density compared to the surroundings. Suppose if it is reverse, below the surface of the earth, you have a spherical ore body with lower density surrounded by rocks with higher density. over there if you carry out profiling, you will end up in having a just reverse of what we are seeing here, right? It will be something like this. You will have a anomaly something like this, because the formation at the center is having lower density compared to the formations around that, right? So, when you carry out interpretation like this, then it is called as direct interpretation, right? That means what the scientists have done is, we ourselves assume certain formations, right? We imagine certain types of formations. For such a formation, what is the gravity value which we will measure at the surface can be theoretically computed, right? So, that is what has been done, which facilitates for direct interpretation by us. That means what we have done, as you see in this picture, here we have assumed a sphere of higher density. The effect of that has been theoretically computed. Then in this diagram, we assume the presence of a horizontal cylinder perpendicular to the screen now. Perpendicular to your screen, there is a cylinder. What will be its impact on the gravity measurements which we will make at the surface? By gravity measurements, I mean acceleration due to gravity, right? We can either do absolute gravity measurements or relative gravity measurements, right, which we have seen already, right? So, what will be the effect of presence of a horizontal cylinder of higher density compared to surroundings? Surrounding is low, the body has got high density. The anomaly will be more or less similar to a sphere, right? So, this is how we can theoretically compute the gravity profile which we will measure at the surface for different buried bodies, right? For sphere and a cylinder, we get more or less the same profile, gravity profile, right? How can we distinguish whether it is a sphere or a cylinder below the surface of the earth, right? So, this is the steady site on which we are carrying out the survey. Imagine beneath here you have a sphere, right? When you do survey this way, you will have a profile like this. When you do survey along north-south, you will have the same profile, isn't it? Because it is a sphere. Imagine now here beneath the surface you have a horizontal cylinder, buried horizontal cylinder with higher density. When you do a profiling from north to south, you will get a profile like this, right? More or less, we may think it is a cylinder. To cross check, now we will do one more survey from west to east. When you do such a survey, your profile will look something like this, isn't it? Because this approximately indicates the length of the cylinder, right? So, we will be able to distinguish cylinder from a sphere by carrying out gravity profiling in two perpendicular directions, right? As I told you, it can be carried out in two perpendicular directions. For such simple bodies, we can estimate its depth of burial below the surface of the earth or its location from the surface of the earth using some relationship, right, based on the anomaly that formation is going to create, right. So, it is possible for us to estimate the approximate limiting depth of ore bodies present below the surface of the earth. So, what is the limiting depth? So, this is the surface of the earth. There is a sphere here, right, which is having high density, right, and here we have low density. The profile which you will, gravity profile will be something like this, because over here gravimeter will measure higher reading. At the surrounding you will have lower values. Why? Because here the formation has got lower density, right. So, we can try to determine what is the depth of this formation from the ground surface, right. Right. Limiting depth is the maximum depth at which top of the body will occur, right. So, this formula help us to determine the maximum depth until which you can expect that anomalous body, right. This can be done by making use of what is known as half anomaly width. What is half anomaly width? Half anomaly width, which is denoted by x subscript half or sometimes as x half, is the distance from the center of the anomaly at which the amplitude of anomaly decreases by half. This is known as x half, right. So, this is the maximum anomaly, the distance at which the maximum anomaly decreases to half of it, right. Let us say the maximum anomaly delta G is 100 milligauss. We have to find out at what distance the anomaly reduces to 50 milligauss. That distance is known as x half, right. So, I repeat, x half is the distance from the center of the anomaly where the amplitude of anomaly decrease by half, right. So, in today's lecture, we had a look into how the gravity data after reduction can be interpreted. First, we had a look into qualitative method of interpretation, wherein we have a look at the gravity anomaly map. Of course, to prepare the anomaly map, we have to deploy some filtering techniques to get rid of the impact of regional structures on the measured value, right. The measured value comprises of both regional as well as local anomaly. There are tools available to segregate them. Using that, we prepared the anomaly map. By looking at the residual anomaly map, we can understand different geological structures as well as formations. Then we have started looking into direct interpretation of understanding the variously sized or shaped bodies present below the surface of the earth. We will continue looking into the same direct interpretation of the different formations as you see here in the next lecture. Thank you.